Monte Carlo rendering systems can produce beautiful images by simulating the physical process of light transport. They do this by estimating a series of multidimensional integrals at every pixel of the image, calculated by taking a set of samples of the scene function with random parameters. When many samples are taken, you get a high-quality result as shown here. Unfortunately, rendering a complex scene like this one can often take up to a day per frame to compute. When the number of samples is very low, the results are extremely noisy and unacceptable for high-end rendering applications. In this paper, we present a simple image space approach that considerably reduces the noise of Monte Carlo renderings and produces results comparable to those with much higher number of samples. We call our approach random parameter filtering. The key idea behind random parameter filtering is that by determining how the values of the samples statistically depend on the random parameters, we can filter out only the noise that has been introduced in the Monte Carlo rendering process. We can explain how our algorithm works with a simple example. Here's a scene we want to render with a depth of field effect, which involves integrating the radiance over the lens of the virtual camera. Monte Carlo rendering systems do this by selecting random points on the lens and summing up the contributions of the radiance through each of these points. If a small number of samples are computed per pixel, say 8, the render will be fast but very noisy. We would like to denoise this image, but it's hard for the rendering system to know where the noise is. After all, it's difficult for the renderer to tell what is valid scene detail and what is noise introduced by the Monte Carlo process. However, if we can establish a statistical dependency between the sample's values and the random parameters, we can determine which samples are noisy and should be filtered. To see how, let's examine a pixel that's in focus. Any ray through the lens from this pixel will land on the same region of the scene, regardless of where on the lens the random point is located. In other words, for these samples, we will find no statistical dependency between the final sample color and the random parameters that select the point on the lens, because the random parameters do not affect the final color at all. Therefore, we know this region is in focus, and we should keep our filter kernel small. For pixels out of focus, on the other hand, the position of the random point on the lens affects the final color of the sample. Here, a statistical analysis of the samples will indicate that the final color has a strong dependency on the random parameter, which is why these regions look noisy in the first place. Therefore, we should filter more heavily in this region to reduce noise. This allows us to produce a noise-free result that is comparable to a high-quality rendering. The idea of reducing Monte Carlo noise by finding the statistical dependency between sample values and the random parameters used to calculate them works for other effects as well, such as motion blur, path tracing, or a combination of effects. This simple idea results in an algorithm that can effectively remove most of the noise of Monte Carlo renderings while preserving important scene features. Details about our algorithm can be found in the paper. To see our algorithm in action, let's look at an animated sequence of the same chess scene. A traditional Monte Carlo rendering system with only 8 samples per pixel outputs noisy images that are even more objectionable when animated. In order to determine the statistical dependence of the sample values on the random parameters so that we can filter these images, our algorithm outputs a set of scene features for every sample. In this example, these scene features include the screen position of the samples, the random parameters which select the point on the lens for depth of field, the world position, normal information, and texture values for the first intersection point, as well as the final sample color. Using this, we use mutual information to find the statistical dependency of the scene features on the random parameters. Note how the noisy regions for each of these features has a clear relationship with the random parameters, while the smooth regions are unaffected by their values. This is the dependency that our algorithm will look for. Our algorithm will compute a normalized dependency map that indicates where we need to blend samples together. Here, the darker red colors indicate regions where the filter kernel should be large, because the scene is out of focus, while the blue color indicates parts that are in focus and should not be filtered. Because our filter is based on the bilateral filter, we're still able to preserve scene detail in regions where we're blending the samples. By doing this, we're able to take a noisy Monte Carlo input as shown on the left and denoise it to remove much of the noise, yielding the results shown on the right. Here we compare our result with a reference image that was rendered with 4,000 samples per pixel. You can see that our result is comparable in quality despite the fact that we had 500 times less samples to work with. We can also compare our algorithm to other modern approaches. Here we show the results produced by our approach and those of the true edge-avoiding filter method proposed by Damertz et al. In HPG 2010, and Overbeck et al.'s adaptive wavelet rendering approach of SIGGRAPH Asia 2009. The ATRU method is unable to identify the important scene features that need to be preserved, and so it has overblurring in certain parts of the scene, while at the same time is unable to filter out most of the depth of field noise. The adaptive wavelet rendering approach, on the other hand, has wavelet-like artifacts in the reconstruction of the scene when the sampling rate is so low. Here's another scene that has been rendered with a path tracer using 8 samples per pixel. The path tracing of indoor scenes tends to be noisy because of the wide range of illuminations possible in these environments. This is the result after our algorithm has been applied. You can see that we have removed much of the noise while preserving most of the important detail, such as the shadows on the wall and the detail on the carpet. Finally, we show the results of rendering the San Miguel model from the physically based ray tracing book using a path tracer. Here's the noisy input to our algorithm that took about 50 seconds per frame to compute. After a few minutes, our algorithm produces frames like this. We keep most of the scene content, such as soft shadows, textures, surface detail, and so on, while removing the rendering noise. Note how we can recover detail even though some of it is not visible in the 8 samples per pixel input data. Here's a side-by-side comparison against the ATRU method. Due to the complexity of this scene, this was the only algorithm that we can compare against. We also rendered a few frames with a high sampling rate for reference. In this case, the reference video was impossible for us to render, since each reference frame took a little over 24 hours to render on a high-end machine. At this rate, the entire sequence would have taken almost a year to render.